Hello, friends. Welcome to the second session of our series on overcurrent and earth fault relaying. We have already discussed in the first session about the fundamental concepts of overcurrent and earth fault relaying. In the first session, we have discussed what are the requirements of overcurrent protection. We discussed about the instantaneous, time delayed, and IDMT overcurrent based protection. We have also discussed in the first session that why different types of IDMT characteristics like moderately inverse, standard inverse, long time inverse, short time inverse, or very inverse and extremely inverse characteristics are required. I hope the concepts discussed in the first sessions are clear to all of you. In case of any doubts, in case of any problem, you can comment in the comment section so that I will try to answer those queries. In this session, we will focus on the fourth topic because the first, second, and third has already been discussed in our first session. In this session, we will basically discuss about the protection coordination for non-directional overcurrent protection only. The protection coordination for earth fault protection shall be discussed in a separate video. Till now, we are discussing about non-directional protection only. So in this session, we will continue with the non-directional protections only. Uh, Now, let us begin with today's session. We have already discussed about these things, how to do coordination with fuse, what is the non-directional IDMT characteristic, definite time characteristic, etc. So now in this session, we will start with the coordination. In this session, we will discuss about the basics coordination philosophies, how to select the minimum current pickup, how to select the time of operations of the overcurrent type relays. Then we will discuss what is the meaning of plug setting multiplier, time multiplier settings, and how to calculate this TMS for one typical example we will discuss in this session. Now, the first uh, topic in today's session is the overcurrent protection coordination principle. We have already discussed in the first session that the basic requirement of any protection system is to isolate the fault as quickly as possible and to isolate only the faulty section so that the other healthy section or other healthy power system remains in service. To achieve this thing, the first basic requirement is the relay closest to fault must operate first. Now, uh, suppose we have a power system, a portion of power system in which we have two relays R2 and R1. For a fault at F1 with a fault current IF1, uh, the relay closest to fault that is R2 must operate first. After R2 fails to clear the fault, or suppose R2 operates but circuit breaker doesn't trips or anything, R2 operates but due to any reason the fault is not isolated, then after the delay of certain time, that time we will discuss is called coordination time interval, the relay R1 should operate and it should isolate the fault. Now if you see R1 is operating after a certain time delay of R2, that means R1 is basically a backup of R2, and whenever there is any backup protection, it will be inherently slow as compared to the primary protection. So in this case, R1 will be slower than R2. Now the question arises, how much slower will the R1 be? The first thing in the coordination is whenever you are going to coordinate any upstream relay with a downstream relay, the coordination is a bit easier as compared to the coordination of upstream relay with a downstream fuse. So that's why we will first discuss the coordination of the relays, that is R1, R2. Now we have generally three things. One is called current setting, then the time of operation, and then the curve type. The first thing in the coordination is your curve type for R2 if suppose it is a standard inverse. And now we have already discussed in the first session when to select a standard inverse, normal inverse. Standard or normal is basically the same thing, extremely inverse or long-term inverse, that and how to select these characteristics. Those things we have already discussed in the first session. Now, suppose the relay R2 is of standard inverse curve type, then R1 must also be SI type. That is the first thing. So curve type is very simple to coordinate. Whatever the downstream relay characteristic is, similar should be the characteristic of the upstream relay. The second thing is time of operation. What should be the time of operation? Now, we know that the time of operation for a relay closure to fault should be minimum. So now suppose in this case the time of operation, now this is only an example, we will discuss what should be the time of operation, but suppose the time of operation of R2 is your 100 millisecond. In that case the time of operation of relay R1 will be time of operation of relay R2 plus certain time delay, coordination time interval. And now we will discuss what is coordination time interval. Basically, what components this type includes. Now, if you see, if there is a fault here, that fault is fed like this. So this relay R2 and R1 both will see the fault current. First of all, R2 should operate. But if you see, when R2 starts at the same time, R1 will also start. When R2 operates, then the first thing is the time of operation of R2. Then, if R2 operates, the next course of action is your breaker should trip. If the breaker trips, that means you have certain time TCB open time. Now, if breaker trips, then your fault current ideally should become zero or closer to zero. But it when your breaker R2 trips, then it takes some time for the uh, current to become zero and this relay to reset, because basically the resetting of this relay depends upon the reset to pickup ratio of this relay. So if the reset to pickup ratio is higher, then this relay will reset quickly. If the reset to pickup ratio is lower, then this relay will take some little bit amount of time to reset. So this time, reset time, will also add in the coordination time interval. Then there are some error time, like some error time or safety margin that we have to kept into picture. So generally, if your T operated to, for if the particular this case, if it is suppose 100 millisecond, then you have this 100 millisecond here plus CB opening time, generally it is 20 to 30 millisecond. Reset time, again it is 30 to 40 millisecond. I am assuming a very conservative approach, and again this error time plus safety margin, suppose it is 150 to 200 millisecond. So the total it adds up to closely 300 to 400 millisecond. That means if you are going to coordinate these two relays, then if this relay, the characteristic is SI, and if its time of operation is zero point 0.1 second, then this relay characteristic will be SI and time of operation will be zero point 0.4 second. That is one thing. Second, if the pickup current for this relay is suppose IS2, then the pickup current of this relay should be slightly more than this IS2, generally 1.1 times or 110%. Sometimes it is also divided by the reset to pickup ratio. For an electromechanical relay, it is closer to 0.95 or 95%. For numerical relays or digital relays, it is 98 or 99%. So now suppose this is the characteristic of the relay R2. So R2 is this relay R2 with characteristic standard inverse. Then when we draw the characteristic of R1, that characteristic of R1 should have a linear CTI at all points. That means it should have a coordination time interval of 300 or 400, whatever we have calculated, at all points over the characteristics of R2. So that means if this is the characteristic of R2, this will be the characteristic of R1. And now if you see, suppose this is the fault current IF1. So for this fault current, this is the time of operation of relay R2 and this is the time of operation of relay R1. So every time the time of operation of relay R1 will be higher as compared to the time of operation of relay R2. So these are the few points, takeaway points from these slides. That is, relay closest to fault must operate first. Other relay must have adequate additional operating time to prevent them operating. If all these relays have same times, then there is a chance that for a fault at this location, R1 will operate and there will be widespread disturbances. Then third thing, current settings should be chosen to allow full load current. That means if I am setting this current I set, it should be more than the full load current. It should never be less than full load current. Generally, it is full load current times 1.1, that is 110% of full load current. And if you are having electromechanical relay, it will be divided by the drop off to pickup ratio. So this should be the minimum pickup current for these relays. Now, the worst case conditions, operating modes and current flows needs to be considered for coordination. Uh, Current flows, the effect of current flow, that is that will be on the directional or non-directional, that we will discuss on a separate session. That is how the current flow decides the coordination and how current flow affects the coordination, that we will discuss in separate slides, separate session. Basically in this session we will focus only on the non-directional relay coordination. Now suppose a simple example. We have these 5 buses EDCBA and there are relays installed at location EDCBA, and suppose we have a fault at location A. Now for this fault location, what should have? First of all, the relay B should operate. If relay B fails to clear this fault, then C should operate, then D, and then E. That means the relay B should be the fastest relay. So suppose we are assuming the standard inverse characteristic. So if this is the characteristic of relay B, then relay C should operate after the time of operation of relay B is suppose this, then relay C should operate at time of operation of relay B plus some coordination time interval. Similarly, time of operation of D should be C plus some coordination time interval. So if you see now, this is the relay B characteristic. C should operate after certain time interval, then D after the certain time interval. Similarly, E after certain time interval. So this is basically a very simple example. Now in the upcoming slides, we will see how to calculate these TMS and other things. And one of the important thing, if you see here, all these coordination, all these TMS and operating time, everything are uh, basically it is calculated based on the fault at the remote bus. First of all, we will consider for the B. Suppose we consider a fault, three-phase fault at the location A, and what should be the maximum fault level. For that maximum fault level, what should be the operating time of B. Similarly, then we will go one step each, like from B to C, C to D, D to E. We will see in the upcoming slides. Now, the another thing is there are different types of characteristics like standard inverse, very inverse, extremely inverse, or long time inverse. All these characteristics, earlier, the time of operations were calculated by using the logarithmic plot of plug setting multiplier or current multiples of the current setting with operating times. Earlier, these were calculated using chart, but now no need to calculate using this. You can directly calculate using the formulas. For example, for the standard inverse case, the time of operation is basically 0.14 times TMS divided by I fault by I set to the power 0.02 minus 1. Now, if you see what is I fault, is basically the fault current, and I set is basically the setting current in the relay. Now, if you see this IF by I set, that means this is basically a multiple of I fault is basically a multiple of set current, and this is also called plug setting multipliers. So Sometimes you can see this IF by I set as I. If you see here, 0.14 divided by I to the power 0.02 minus 1 into TMS will be your time of operation of a standard inverse characteristic. Now, what is the meaning of this plug setting multiplier? What is the meaning of time multiplier setting? I have already explained to you what the meaning of plug setting multiplier. Basically, plug setting multiplier is the multiple of the fault current, which is a multiple of set current. This is basically plug setting multiplier. Now, if you see, the relay operating times can be calculated using relay characteristic charts, but nowadays no need to calculate using characteristic chart. You can directly calculate using the formulas if you want to calculate. Second thing, uh, the published characteristics are drawn against a multiple of current setting or plug setting multipliers. So these are good old days when these were calculated like this. And depending upon which type of characteristic we are using, we will have different types of curve. We will have different types of operating time. So same thing we can calculate using mathematical formula. Now, this thing, the current setting, I have already explained that the operating current should be set just above the full load current with a 10% tolerance. That means the I operating current should be set 1.1 times of I full load current. Uh, Now, if we have two relays like this, we have one relay here and we have one relay here. And if we want to set the current for this relay, then this relay, we have to also allow the relay to reset if fault is cleared by downstream feeder. So, for example, if there is a fault at this location, this relay will also pick up. But if the fault is already cleared by this relay, then this relay should not operate. So that is, if the fault is cleared by downstream feeder, then the relay should reset, and that comes from the your drop off by pickup ratio of the relay, or also called reset to pickup ratio. Reset to pickup ratio. Generally, for modern numerical or digital relay, it is from 95 to 99%. With electromechanical or relays, in earlier days it was in 90 to 95%. So depending upon which type of relays we are using, we can calculate. For example, for numerical relays with drop off to pickup ratio of 95%, the set current should be 110% of full load current divided by the drop off to pickup ratio, which is 0.95. Now, uh, if you have calculated the current grading for this relay, suppose this relay, the current operating current that I set comes to suppose 100 ampere, then this relay should be slightly higher than R1, and that we can set like I said as 1.1 times so 100. This is basically done if you are using only current grading. So only current grading system, we can just grade the current of the upstream feeders like this. If it is 100, the next would be 110, next would be like 110% of 110. Now, what is the grading margin? Grading margin, it is same like thing which is I have already discussed, which is coordination time intervals, and this is the operating time difference between two devices to ensure that downstream device will clear fault before upstream device trips. Basically, the fault relay closure to the fault should operate. That means if the fault is in the uh, suppose this is a power system and fault is here, then the relay closer to this, that is this relay should operate. This is called downstream relay for this upstream relay. So uh, this coordination time interval or grading margin basically consists of breaker opening time, allowance for error, relay overshoot, and safety margin. This we have already discussed. So now consider these two relay of in a power system, the relay R2 and relay R1. So now if the R1 relay has R2 relay basically, because this is we are considering fault here. So suppose this R2 relay, this relay has the characteristic like this. R1 relay characteristics should also be same, but what should be this difference? This is the grading margin or coordination time interval. What should be this? So this basically depends upon breaker opening time, relay overshoot, some error, and safety margin. Relay overshoot, and then these errors basically it constitutes of your reset time of the upstream feeders. So nowadays breaker opening time is generally in the range of 20 to 30 millisecond. Uh, Other things you can consider 30 to 40 milliseconds, and a safety margin of 150 to 200 millisecond may be considered for a numerical relay. So This will comes approximately 200 to 300 millisecond as grading margin. That means 0.2 to 0.3 seconds. So if we are very conservative, and if nowadays we can assume that this grading margin this is 0.3 second. Uh, if we have electromechanical relay, we can assume this as 0.4 second also. But generally for numerical relay, the grading margin of 0.3 second is more than enough. Now, how to coordinate overcurrent relay with a fuse? A coordination of overcurrent relay with another overcurrent relay is very simple because we have a characteristic of a downstream relay, and we can select the same characteristic of an upstream relay with some grading margin or with some coordination time. But if we have a fuse downstream and if we want to coordinate our this relay with this fuse, then the coordination is very difficult because we know that a fuse have a very different types of characteristic. It will operate for a certain current. If the current crosses that limit, the fuse will blow, fuse will melt down after a very short time, like suppose 10 to 15 milliseconds. So fuse have these type of characteristics, and if we want this relay to coordinate with this fuse, so what we want this characteristic to have a sufficient grading margin all along this relay, all along this fuse. Even if suppose we are considering this grading margin at this point as 0.3, we cannot have the sufficient, we cannot have the exactly same characteristic all over, because now if you see this time will be more as compared to this time. So generally, for if we want to coordinate with fuse, we have to select, if this is fuse, the relay characteristic should be very inverse or extremely inverse. The current for this overcurrent relay should be 3 to 4 times the of fuse current, that the rating of the fuse. Now, what is the meaning of time multiplier setting? Time multiplier setting is basically used to adjust the operating time of an inverse characteristic. It is not a time setting, but a but simply a multiplier. So, it the TMS is calculated to give desired operating time in accordance with the grading margin. So, whatever our grading margin is, we can calculate a TMS to give a desired operating time, whatever operating time that we want. For example, for the same condition, suppose this relay has time of operation of 1 second with any TMS of suppose 0.05. Now, if this relay operating time comes out to be zero point 0.1 plus grading margin of suppose zero point 0.4, this relay comes out to zero point 0.5 second. So now basically what is TMS? TMS is a multiplier setting that we have to select in such a way that the operating time of this relay comes out to zero point 0.5 second with a characteristic standard inverse if this characteristic is standard inverse. So now how we do this calculation. So we will try to understand this with a one very simple example. So first of all, how to calculate this? So first we have to calculate the required time of operation with grading margin and fault level. Whatever the fault level is given, we have to calculate the required time of operation. Then we have to calculate the operating time of an inverse characteristic with a TMS 1. So this inverse characteristic can be standard inverse, very inverse, extremely inverse. So keeping TMS equal to 1, we have to calculate the time of operation, and then the TMS will be the required time that we required divided by the time of operation using TMS equal to 1. So the procedure involves basically to calculate the required operating current, then grading margin, then the required operating time, then select the characteristic, then calculate required TMS, and the characteristic should be such that the grading is over the whole curve. Uh, when we draw the grading curves, it should be drawn on a common voltage base. For example, if we have a transformer in between, any transformer of suppose 132 by 33 kV or 765 by 400 kV. So if we are drawing the curve, all the curves should be drawn at the same voltage level to have a comparison. So now consider a very simple example. We have a portion of power system with two buses, bus B, bus A, and we have a relay installed at bus A, like relay A and a relay B here, with a CT of 200 by 5 here, 100 by 5 here. We have a maximum fault current at this location of 1400 ampere. The relay A is set at 500 ampere, so is the relay B. The TMS of relay A is 0.05 with characteristic SI. We have to coordinate relay B with this relay A. So now, first of all, the first thing is coordinate means what? Coordinate means we have to calculate the TMS for this relay. So for calculation of TMS, what we need? We need to calculate the time of operation of this relay. So to calculate the time of operation of this relay, what we need? We need the time of operation of this relay. So if we calculate time of operation of this relay, then we can calculate the time of operation of this relay is equals to time of operation of relay A plus some grading margin. In this case, we have this grading margin of 0.4 second. So if we calculate this time of operation, suppose x, so the time of operation of this will be x plus 0.4. And now if we have time of operation, we already know the curve here is simple inverse, standard inverse. So this curve will also be standard inverse. So we can calculate the uh, TMS. Simply we will put with TMS 1 what is the time of operation. So with TMS1, time of operation will be 0.14 into 1 divided by this IF by I set to the power 0.02 minus 1. And then we already know the required time of operation. The required is equals to x plus zero point 0.4. So we can simply calculate the TMS is equals to x plus 0.4 required time divided by whatever this TOP is. So now let us see how to do this. So if you see this for this IF, this maximum fault current of 1400 ampere, this relay is set at 5 ampere. That means what is the I set? I set here is 5 ampere. I set here also is 5 ampere. What is the fault current? IF. In terms of secondary, it will be 1400 divided by 100 by 5 CT ratio. So it will be 70 ampere. What is the I fault here? It is 1400 because same fault current for both divided by 5, so it is 35 ampere. So now first we will calculate the time of operation of this relay, which will be 0.14 times TMS divided by I fault, that is 70, divided by I set, that is 5, to the power 0.02 minus 1. So if you see here, 0.14 into 0.05, that is this, divided by 14, that is 70 by 5, to the power 0.02, that is this, minus 1. So this comes out to be 0.13. That means the time of operation of relay A is 0.13. So the required time of operation of this relay is equals to 0.13 plus a grading margin of 0.4, that is 0.53, and the curve will be standard inverse. So this is the time of operation of relay B with standard inverse curve. So now what we have to do? First we have to calculate the time of operation of this relay with TMS is equals to 1 and with standard inverse characteristic. We also know IF here we have already calculated at 35 ampere and I set is 5. So we can very simply calculate for operate TMS equal to 1. The time of operation will be 0.14 into TMS divided by IF by I set, that is 35 by 5 to the power 0.02 minus 1, that is 0.14 into 1, that is 0.14, divided by the 35 by 5, that is 7 to the power 0.02 minus 1. So 3.52 is your time of operation when you are assuming TMS equal to 1. But what is the actual time of operation required? Actual time of operation required is 0.53. So the required TMS will be 0.53, that is the time of operation required, divided by TMS at 1, that is 3.52, the operating time at TMS 1. So it will come out to be 0.15. So for the coordination, this relay will have a standard inverse with TMS is equals to 0.15. So now if you draw the characteristic of suppose relay A, so if this is my relay A, the relay B will be like this because it will be also the standard inverse and this time is your 0.4 second. So I hope the concepts which are discussed in this session are clear to all of you. In case of any doubt, you can ask in the comment section and We will meet again in the next session. We will discuss about earth fault protection. Thereby, we will discuss about the need for the directional overcurrent protection, directional earth fault, the coordination in case of parallel feeders, coordination with two sources, coordination with multiple sources. All these things we will discuss in the upcoming sessions. I hope the concepts which are discussed in today's sessions are clear to all of you. If you think that this video is helpful to you, then you can share this video with your friends so that they can also get benefited with these concepts. So, thank you. We will meet again. Till then, thank you and goodbye.